This is David Spears, civil engineering instructor at Texas Tech University, talking about CE 3303 solids. Got a little video here on shear stress, transverse shear stress, the actual true shear stress, as opposed to average. And got a shape here. It's a channel or a C-shaped section. And in another video, I did a calculation of y bar and the centroidal moment of inertia I bar x prime in this orientation. And I got those two values that are given, 2.038 inches for y bar and Ix is 30.31 inches to the fourth. Look at that other video if you want to see how to calculate those things. Okay, so what we're dealing with is shear stress, transverse shear stress. Remember that shear is a force that's parallel to a surface, so it's parallel to this cut. And this transverse shear is a phenomenon that exists in beams due to bending. And it's a very important force and stress to design for, so we need to understand it. And it's got a lot of geometry in it. The basic formula is shear stress tau, which is, remember, a stress is a force divided by an area, is this basic formula VQ over IT. Okay, in that formula we have four variables. V is the shear force, and that is parallel to the cut surface and it's perpendicular to the neutral axis of bending. For us, the neutral axis is this x prime centroidal horizontal axis. Let's get to Q in here in a second. I down the bottom is the moment of inertia about that neutral axis. We have, remember, a bunch of moments of inertia. Two primary ones that we think of for symmetrical shapes. And anyway, this is the moment of inertia about the x prime axis, that horizontal axis that is perpendicular to the shear force. Then we have on the bottom also the variable t, which is the thickness of the section where the shear stress tau is being calculated. And then back to the top we have that capital Q, which is really two numbers multiplied together, y bar prime and a prime. First, let's define A prime, as I've done here in red. It's the area of the cross-section away from the neutral axis. We'll see more what that means when we do the calculation here. And Y bar prime is the distance from the centroid of A prime, that area, to the neutral axis. So let's do a problem and see what some of those things mean. Okay, so I want to find the shear stress at 3 points on this section. The first one is D, shown in red, and it lies just above that little inside corner where the vertical leg meets that horizontal part, right there. So by that I mean it lies in the horizontal part, but just barely. And so, let's figure out what those variables are for this problem and solve for the problem. Find the shear stress there at that point. Okay, if I'm dealing at point point D, then V is going to be 10 kips and I is going to be that moment of inertia that's given. T we'll talk about here in a second, but let's talk about Q first. Okay, Q is A bar, Y bar prime, A prime. So A prime, area prime, is the area away from the neutral axis at the point where I'm calculating the shear stress. So I'm going to draw that area. I'm calculating the shear stress at point D, and so A prime is going to be the area of that horizontal rectangle at the top. So that's A prime. A prime for this shape, it's 5 inches wide and 1 inch tall, so it's 5 times 1 is 5 square inches. Y bar prime is the distance from the centroid of that, which let me draw a little blue cross there. The centroid of A prime is right there. And this thing is 1 inch tall, so that makes it a half an inch below the top. It's half of the height of the rectangle. Y bar prime is the distance from the neutral axis to that point, to that centroid. So that's Y bar prime. Y bar prime, therefore, is the centroidal distance from the top is 2.038 to the neutral axis. This is the neutral axis. 2.038 minus 0.5. So that's 1.538 inches. Okay, the other thing I need to know is T. T is the thickness of the cross section where tau, shear stress, is being calculated. So for point D, which is barely into that horizontal rectangle, T is this entire width of the section, 5 inches. So now I know all my numbers, so I can calculate my shear stress at D. So that's tau at D is VQ over IT. V is 10 kips. Q is Y bar prime, 1.538, times A prime, which is 5 square inches. So this is kips. This whole thing multiplied together is Q, and that's in inches cubed. On the bottom I have I, 30.31, and the thickness at that section is 5 inches. Do the math, and that works out to be 0.0508 kips per square inch, or KSI as we usually call it. So that's one answer. Now I want to know, back to the drawing, I want to know the shear stress at point E, which is just barely below the corner. So it's going to have essentially the same Q, but a different T thickness. For E, while I'm looking at it, and it's clearer on this picture, T is going to be the thickness at this section right here, but it also includes this section over here in green. So I've got the 1 inch over here and the 1 inch over here. So the shear stress all along that point, barely into that vertical leg below that corner, the T is going to be 2 inches. So I can do the calculation. Q is still the same because I'm like in the calculus way, just barely into the section below that corner. So Q is the same. So tau at E is the same VQ 10 1.538 times 5. I is still the same, 30.31. And the thickness now is 2 times 1. So that makes the number work out to be 1.269 KSI. So make that small little distance between D and E causes the shear stress to jump up quite a bit because I have a much thinner shape or section to transfer that shear stress at. Transverse shear force. Finally, I want to know the shear stress, tau, at the neutral axis. So I showed it up here at point F, lying right on the neutral axis, which that is. Therefore, I have a different Q. And I could pick either section. Q is defined as y bar prime A prime, where A prime is the area away from the neutral axis where I'm calculating the shear stress. So I could do it the hard way, which is figure in blue this area, this little C-shaped area. Figure that A prime. Then I have to figure out the centroid of that A prime, which I don't know where it would lie, something like right there. So that would be one A prime, and that would be a Y bar prime. But a much easier thing is to calculate the area A prime and Y bar prime of this section in red below the neutral axis. Once again, it's away from the neutral axis, this is just below. So it's both of these vertical legs, these segments of them. So it's the area I'm shading in red. So the area of those two things, okay, I need to observe that if y bar is 2.038, this y distance at the bottom is just 5 minus that distance. So it's 2.962 inches. So that's the height of that rectangle. The rectangles are 1 inch wide, both of them. So therefore, A prime is just going to be 2, because there's two rectangles. They're 1 inch wide, and they're 2.962 inches tall. So therefore, A prime is 5.923 inches squared. Last thing I need is y bar prime. Y bar prime is the distance from the centroid of that area, which is right here, both those rectangles. So it's an easy calculation. It's just half the height of the rectangle. So this is the y bar prime I'm going to use here. And y bar prime is just going to be half of 2.962. It's a rectangle, half of its height, 1.481 inches. Therefore, I'm ready to calculate tau. Real quickly, let's note again that the thickness at that section is the thickness of one leg of the rectangle, one rectangle, and the other rectangle 1 inch. So it's a total of 2 inches thickness. Therefore, tau at the neutral axis, tau at F, is equal to V, 10, Q, which is y bar prime, 1.481, times A prime, 5.923, divided by the same I, 30.31, and T is 2 times 1. Therefore, I get that is equal to 1.447 KSI. Okay, it's interesting to plot these things on the cross section. Plot the shear stress as it varies up and down the section. At the top, I've got 0. At the bottom, I've got 0 shear stress because Q is 0. Here at this point D, I had 0.508 KSI. At point E, barely into the vertical leg, I jump up to 1.269. And then here at the neutral axis, the shear stress is 1.447 KSI.